Far out along the floor of the northeastern Pacific Ocean, a dense slab of seafloor is sliding beneath the edge of North America at a pace of roughly 1.5 inches, about 3.5 centimeters, every year. The motion is slow enough to escape human perception entirely, yet relentless enough to build mountains, generate earthquakes, and feed one of the most dangerous volcanic chains on Earth. From Northern California through Oregon and Washington into British Columbia, the Cascade Range rises in a line of snow-capped peaks that often appear calm, stable, even dormant. But beneath those volcanoes, scientists continue detecting signs that the system is neither extinct nor asleep. Heat still moves upward, magma still forms, fluids still circulate through fractured rock deep underground. Seismic instruments still record bursts of movement beneath several volcanic centers. The silence itself has become part of the concern. Why has such a massive volcanic arc remained comparatively quiet for so long? Is the calm merely a pause in a geological cycle, measured not in years but in centuries? Could the Cascades already be shifting into a new phase of activity, so gradual that the public barely notices it happening? Those questions have increasingly shaped modern volcanic monitoring across the Pacific Northwest as researchers track subtle changes beneath mountains that have produced some of the continent's largest eruptions. For many residents of the western United States and Canada, the Cascade volcanoes exist more as scenery than as active geological systems. Mount Rainier towers over the Seattle metropolitan region. Mount Hood stands above Portland. Mount Shasta dominates Northern California. Crater Lake attracts tourists who often do not realize they are looking into the collapsed remains of a volcano that produced one of the largest eruptions in North American history. Snow, glaciers, forests, and hiking trails create an impression of permanence. Yet every major volcano in the Cascades is geologically young and remains capable of erupting again. The chain exists because of subduction. Offshore, remnants of the ancient Farallon Plate continue diving beneath North America. Those fragments are now known as the Juan de Fuca Plate, the Explorer Plate, and the Gorda Plate. As the oceanic crust descends into the mantle, water trapped within minerals inside the slab is released by increasing heat and pressure. That water lowers the melting temperature of surrounding mantle rock, allowing magma to form. Some of that magma rises toward the surface, collecting in chambers and reservoirs beneath the volcanic arc. The process has operated for millions of years. During that time, the Cascades have generated enormous eruptions, widespread lava flows, collapsing volcanic domes, ash clouds, and destructive mud flows known as lahars. Entire volcanic edifices have failed catastrophically. Rivers have been buried beneath volcanic debris. Ancient forests have been entombed in ash and mud. Modern civilization in the Pacific Northwest developed during one of the quieter intervals in the range's eruptive history. That historical coincidence may have distorted public perception of risk. A widely discussed analysis published by Wired examined how unusual the relative quiet of the past century has been compared with the broader geological history of the Cascades. The report noted that only one Cascade volcano, Mount St. Helens, erupted during the past 100 years, despite the range containing more than a dozen major volcanic centers. Yet when researchers examine longer timelines extending back several centuries or several thousand years, the apparent silence becomes less extraordinary. Mount Hood, Mount Rainier, Mount Shasta, Glacier Peak, and Mount Baker all erupted within the past few centuries. Lassen Peak erupted in the early 20th century. The eruption of Mount Mazama, roughly 7,700 years ago, created the caldera now occupied by Crater Lake after one of the largest volcanic explosions ever recorded in the region. From a geological perspective, the Cascades are not inactive. They are intermittent. That distinction matters enormously. Volcanic systems do not behave according to human expectations of time. A volcano can appear motionless for centuries while magma slowly accumulates at depth. Chemical changes can occur in subterranean reservoirs long before any visible eruption develops. Faults can fracture gradually. Hydrothermal systems can shift over decades. Heat can migrate upward through crustal rock without producing immediate surface activity. Scientists studying volcanic arcs have increasingly emphasized that long quiet intervals do not eliminate danger. In some cases, prolonged dormancy can actually allow larger volumes of magma to accumulate before an eruption finally occurs. Research published through the United States Geological Survey has shown that volcano-tectonic earthquake swarms frequently precede eruptions at volcanoes that have remained dormant for decades or longer. These seismic events often represent magma forcing its way through fractured crust, generating stress changes far from the eventual eruption site itself. The Cascades possess many of the ingredients necessary for renewed activity. Deep magma generation continues because subduction offshore has not stopped. Heat flow persists beneath volcanic centers. Gas emissions continue at fumaroles and hydrothermal vents. Seismic monitoring occasionally records earthquake swarms beneath individual volcanoes. The challenge is that most of these processes unfold gradually and irregularly. At Mount Rainier, for example, seismic instruments regularly record small earthquakes. Many are tectonic, some are associated with hydrothermal circulation. Others may reflect subtle stress adjustments inside the volcanic structure itself. The mountain is heavily glaciated, adding another layer of complexity because glacier movement can also generate seismic signals. Rainier's greatest danger may not even come from a large explosive eruption. The volcano contains immense quantities of ice and hydrothermally weakened rock. Even a relatively modest disturbance could generate fast-moving lahars capable of racing down river valleys toward populated areas. Geological evidence shows that such flows have occurred repeatedly in the past. Further south, Three Sisters has drawn scientific attention because of measurable ground deformation detected through satellite observations. Parts of the volcanic complex have experienced uplift over recent decades, suggesting magma or hot fluids may be accumulating beneath the area. The uplift has occurred slowly, measured in inches over many years, yet it demonstrates that the subsurface system remains dynamic. At Mount Baker, increased heat and gas emissions in the 1970s raised concern about possible unrest, although no eruption followed. Scientists later concluded that hydrothermal activity had intensified without progressing toward eruption. The episode nevertheless reinforced how active many Cascade volcanoes remain beneath their outwardly tranquil appearance. Even volcanoes without recent eruptions continue venting gases through fumaroles and hot springs. Those emissions provide important clues regarding magma movement below the surface. Hydrothermal monitoring, conducted by the United States Geological Survey across several Cascade volcanoes, established long-term baseline measurements, specifically because scientists recognize that future unrest may first appear through subtle temperature shifts, changing gas chemistry, or variations in groundwater systems. The phrase "waking up in slow motion" reflects that incremental reality. There is no evidence that the entire Cascade Range is approaching simultaneous eruption. Volcanic systems behave independently, each with its own plumbing structure, magma supply, and geological history. But there is growing recognition that the apparent calm of recent human history may not represent the long-term norm. Part of the reason the Cascades appear quieter than volcanic arcs around the Pacific Rim involves tectonic geometry. Compared with regions such as Japan, Indonesia, or the Kamchatka Peninsula in Russia, the Cascadia subduction system operates differently. The Juan de Fuca plate descends more steeply beneath North America and at a slower convergence rate than some other major subduction zones. Researchers have suggested that these differences may influence magma production and eruption frequency. The oceanic crust entering the Cascadia Trench is also relatively young compared with crust subducting beneath parts of Asia. Younger oceanic crust tends to contain less water absorbed over geological time, potentially affecting how much fluid becomes available to trigger mantle melting. These tectonic factors may partly explain why the Cascades generally erupt less frequently than volcanoes in places like Alaska or Indonesia. But less frequent does not mean safe. The eruption of 1980 eruption of Mount St. Helens demonstrated how devastating even a single Cascade eruption can become. On May 18, 1980, a magnitude 5.1 earthquake triggered the collapse of the volcano's northern flank. The resulting lateral blast flattened forests across roughly 230 square miles, about 600 square kilometers. Ash spread across multiple states. Rivers were choked with sediment. 57 people died. The eruption transformed volcanic monitoring in the United States. Before 1980, many Americans viewed volcanic disasters as distant events associated mainly with other continents. After Mount St. Helens erupted, the Cascades became recognized as a major domestic hazard zone. Yet as decades passed without another large eruption, public attention faded again. Scientists did not stop watching. Today, the Cascade Volcano Observatory and associated monitoring networks maintain extensive systems of seismometers, satellite measurements, gas sensors, deformation instruments, and remote cameras. Researchers analyze ground uplift, earthquake swarms, thermal anomalies, and changes in hydrothermal circulation. Continuous data streams allow scientists to identify subtle patterns that would have been invisible only a few decades ago. Modern volcano monitoring increasingly focuses on detecting precursors that emerge gradually over long periods, rather than expecting sudden dramatic warnings. One important lesson from global volcanology is that magma intrusion often does not culminate in eruption. Magma may rise partway through the crust and stall. Pressure can redistribute underground without breaching the surface. Earthquake swarms can occur without visible volcanic activity. Ground deformation may continue for years before stabilizing. This uncertainty complicates hazard forecasting. Researchers have worked to improve interpretation of volcanic seismicity, partly because dormant systems can reactivate with limited warning. United States Geological Survey research examining volcano-tectonic earthquakes found that seismic swarms frequently represent some of the earliest indicators of magma intrusion. At the same time, scientists caution against interpreting every earthquake swarm as a sign of imminent eruption. The Pacific Northwest is tectonically active, even apart from volcanism. Fault movement, crustal stress changes, and glacial processes all contribute to regional seismicity. Public fascination with volcanic danger often surges whenever earthquake clusters occur beneath Cascade volcanoes. Social media speculation frequently outruns scientific evidence. Researchers therefore emphasize distinguishing between ordinary background activity and patterns that genuinely indicate escalating unrest. That distinction is not always simple. Volcanoes are extraordinarily complex systems, shaped by interacting processes involving rock mechanics, fluid movement, gas pressure, heat transfer, and tectonic stress. Even with modern instrumentation, forecasting the exact timing of eruptions remains extremely difficult. Scientists can identify elevated unrest. They can detect magma movement. They can estimate probabilities. But predicting precisely when an eruption will occur remains beyond current capability in many cases. This uncertainty creates a strange tension across the Pacific Northwest. Millions of people live within reach of Cascade volcanic hazards, yet daily life proceeds with little awareness of the geological systems looming overhead. The region's population has expanded dramatically since the 19th century. Urban development now extends into valleys historically shaped by volcanic mudflows and ash deposits. Transportation corridors, reservoirs, hydroelectric infrastructure, and agricultural systems all intersect terrain influenced by volcanic history. In Washington state alone, lahars from Mount Rainier represent one of the most serious volcanic hazards in the United States because of the number of communities located downstream. Geological records show that large mudflows from Rainier have repeatedly traveled dozens of miles from the volcano. Unlike lava flows, lahars can move with terrifying speed through river valleys, carrying boulders, trees, sediment, and water in dense, destructive torrents. Even volcanoes that erupt infrequently can therefore produce catastrophic impacts when conditions align. Ash hazards present another major concern. Fine volcanic ash can damage aircraft engines, contaminate water supplies, disrupt power systems, impair visibility, and create respiratory problems. The 1980 Mount St. Helens eruption deposited ash across huge portions of the western and central United States. A future eruption from another Cascade volcano could produce similarly widespread disruption depending on wind direction and eruption intensity. Scientists also continue studying how tectonic earthquakes and volcanic systems interact. Large earthquakes can alter stresses within volcanic regions and occasionally influence hydrothermal systems or local seismicity. United States Geological Survey research has noted that while direct earthquake-triggered eruptions are relatively rare, major seismic events can perturb volcanic systems in subtle ways. That relationship is especially relevant in Cascadia because the offshore subduction zone itself is capable of generating massive megathrust earthquakes. Geological evidence indicates that the Cascadia subduction zone has produced giant earthquakes and tsunamis repeatedly over thousands of years. The volcanic arc and the megathrust system are linked by the same underlying tectonic engine. Deep beneath the Pacific Northwest, oceanic crust continues descending into the mantle exactly as it has for millions of years. Heat continues rising, rock continues melting, magma continues evolving chemically underground. From the perspective of Earth processes, the Cascades are active every day. The quietness visible at the surface can therefore be misleading. Satellite technology has transformed understanding of these volcanoes during the past several decades. Interferometrics synthetic aperture radar, commonly called INSAR, allows scientists to detect subtle surface deformation across broad regions. Ground movement measuring only fractions of an inch can reveal pressure changes deep underground. At volcanic systems such as Three Sisters, this technology revealed uplift patterns that might otherwise have gone unnoticed in remote terrain. Similar methods are now applied globally to monitor volcanic unrest. Gas monitoring has also advanced significantly. Carbon dioxide, sulfur dioxide, helium isotopes, and other emissions help scientists evaluate whether magma is degassing at depth. Because gases can escape from magma long before molten rock reaches the surface, changes in emissions sometimes provide early clues regarding subsurface activity. Hydrothermal systems offer additional windows into volcanic behavior. Water circulating through hot rock can transport heat and dissolved chemicals upward. Monitoring spring temperatures, fumarole activity, and groundwater chemistry helps establish baseline conditions against which future changes can be measured. The emphasis on baseline monitoring reflects another important reality. Detecting volcanic unrest requires understanding what counts as normal in the first place. Many Cascade volcanoes constantly generate small earthquakes, emit gases, and sustain hydrothermal circulation. Scientists therefore focus not merely on activity itself, but on deviations from long-term patterns. An isolated earthquake swarm may not mean much. Sustained escalation combined with ground deformation and changing gas emissions would attract far greater concern. This gradual, data-driven approach differs sharply from popular portrayals of volcanic disaster, which often focus on dramatic explosions rather than the prolonged periods of subtle change that usually precede major events. The idea that the Cascades could be waking up in slow motion does not imply that eruptions are imminent tomorrow or next year. Instead, it reflects growing awareness that volcanic systems evolve continuously beneath the surface, and that recent historical quiet may represent only a temporary lull within much longer eruptive cycles. Geological history strongly suggests the Cascades will erupt again. The only uncertainty is when, where, and how large those eruptions will be. Some future events may be relatively minor lava eruptions in remote wilderness areas. Others could involve explosive ash-producing activity. Still others might primarily generate lahars or dome collapses. Each volcano possesses its own hazards, depending on magma chemistry, glacier coverage, structural stability, and surrounding topography. The Cascades are sometimes described as deceptive volcanoes precisely because they can remain inactive for long intervals between eruptions. Dormancy creates complacency. Forests regrow, glaciers reform, human settlements expand. The volcanic landscape appears stable again. Then geological time reasserts itself. Evidence of earlier eruptions remains scattered across the Pacific Northwest for those who know where to look. Thick ash layers preserved in lake sediments. Ancient lahar deposits underlying modern towns. Lava flows cutting through forests. Crater rims partially erased by erosion. Entire calderas filled with water. The mountains preserve their own history of recurring transformation. Modern monitoring cannot prevent eruptions, but it can improve warning times and hazard planning. Since 1980, volcanic surveillance in the Cascades has expanded enormously. Emergency management agencies now maintain lahar warning systems in some high-risk valleys. Hazard maps identify regions vulnerable to mudflows, ashfall, pyroclastic flows, and debris avalanches. Scientists stress preparedness precisely because the long, quiet intervals can lull populations into forgetting that these volcanoes remain active. In many ways, the greatest challenge may be psychological rather than technological. Humans tend to judge risk based on recent memory. A volcano that has not erupted within living memory feels inactive even when geological evidence proves otherwise. The Cascades embody that contradiction. Snow-covered peaks dominate postcards, tourism campaigns, and skyline photographs. Yet beneath those mountains, the tectonic engine of the Pacific Northwest continues operating exactly as it always has. Oceanic crust still sinks into the mantle. Magma still forms. Pressure still accumulates. The volcanic arc has not shut down. It is merely moving according to timescales far older and slower than human civilization itself.